I'm gonna go ahead and throw my headphones in as well. I feel like it just helps with the audio. Off, done. View. Okay, get the student. Okay, let me hit save so I don't lose my work for taking you guys' attendance, because that happens sometimes. And I'm going to go ahead and share my screen. Start the broadcast. Come on. Okay. So let's see. Sorry for being late, guys. Just, adulting stuff. Let's see. So we are at the end of week 5, right? So that what that means is that we'll have exam 1 should become available this upcoming Wednesday. So today we're doing the last section of chapter 2, which is section 2.6. All of next week will be devoted to the exam. So more than likely, I'll just be available for questions next week. So the exam should become available, I think this upcoming Monday, right? It should be available this Monday at the start of class, and it'll be due the following Monday at the start of class. As a heads up, I'm pretty sure I set prerequisites for the exam in the form of, in order to access the exam, you got to score at least 50% on the corresponding quizzes. So quizzes for weeks 1 through 5, you need at least 50% just to access the exam. But I think in order to access the quizzes, you got to get 50% on the corresponding homework assignments, right? So if you're not caught up, you want to get caught up so that way when the exam is available, you can maximize your time, right? If you wait to the last minute and you try to open that exam, it's not going to be available, all right? And then it can create like a whole clusterfuck, right? Okay. And again, just as a reminder, so class time, the real intent of class time is for it to be a Q&A or a study session. I just go through the homework to just fill the dead air, right? So class time is really the intent that I built for it to be. It's kind of like office hours or a study session. So, I think for you all, it would be best if you ask questions, but again, you don't have to, you're not obligated to do that. All right, let's see. So I can't think of anything else. So what we're going to do is go to section 2.6 and kind of start making our way through some of those concepts, all right? Let's see. How many questions does it tell us? Okay, we got it like 21 questions. Okay, that's fine. So this, actually, I'm going to skip this one because I want to jump to something that's from section 2.6. So that's like a review. These first couple of questions are like review questions, which honestly is not a bad idea, especially since we have an exam coming up. So I'll probably come back to this, but I do want to start with section 2.6. Okay. So this question says, find an exponential function. Let me check one other thing. Let's check. I knew we had somebody in there. Okay, let me go ahead and get them. Let's go to edit. Okay, cool. Yeah. So, I wonder if our heavenly friend is gonna be practicing her river dance today during class. She's been doing it pretty consistently. It's kind of funny. Again, because like math is all about pattern recognition, and then it just seems like it'd be so quiet like all the time. And then when I go to stream during you all's class, she wants to practice river dance or stomping cockroaches or something. I don't know what she's doing. Hopefully she's not stomping cockroaches because we don't want bugs in the building like that. Anyway. All right. Find an exponential function of this form, P of t equals P naught. Okay, P naught n to the power of t over t. Okay, that models the situation, and then find an equivalent exponent model of this form. Okay, it says find an exponential of this form, and then find an equivalent exponential model of this form. Doubling time of 3 years, initial population of 500. Let's see. Like the second one, I feel like I could do. Let me see. Find an exponential function of this form. Okay. Doubling time is 3 years and initial population of 500. So there's a couple of things at play here, right? It says the initial population, so that would be our P naught is 500. And then in the lecture, we kind of discussed this notion of doubling time and half-life, right? It kind of boils down to the same formula, just with the minor adjustment, a minor twist. The doubling time, I think, is like KT equals the natural log of 2. So it's like the rate times the doubling time equals the natural log of 2. So then we would say 3K equals the natural log of 2. So we could find, sorry, 3K would equal the natural log of 2. So we can solve for K. They give us an initial population. Let's see, T is the doubling time, okay. And N. Okay, let's give this a go. Okay, so what I'm gonna do, because I'm trying not to look at the question help, and I kind of automatically want to jump to that second equation, but I'm like, okay, I'm trying to put it together to answer that first part. But so we got a copy. All right, let's look at this. So first, let's make a note of what they're giving us, right? So it says the doubling time. Usually the doubling time is like expressed. Did you die? You were totally charged before. I don't know what this means. Okay, that's what it sounds like. Yeah, you should be fully charged. Okay. So now, usually the doubling time. Oh, then it's still doing this. Let's try one more time. So my Apple Pencil is on the fritz a little bit. I don't know. It just started kind of acting weird. It's fully charged and it's kind of bizarre. So the doubling time we usually express as like the capital T, right? We're just going to say it's 3 years. It says the initial population of 500, so the P naught is going to be 500, right? So it says find an exponential function of this form. So the first one that they're asking us to find is P of T equals P naught n to the T over T. So something per year. Okay. We got the doubling time. We got the initial conditions. Okay, I think that's it. All right. So we can say P of T, P naught is 500. I'm just plugging that in. N, I'm going to leave the N for right now. Little t we don't have, and I don't think they give us information to find it. But capital T should be 3, right? So then we can say T by 3. Let's try this, right? And if this doesn't work, we'll look up and see what we're missing, right? Because sometimes these just want just that part, right? It's not, they don't want you to all the way. Okay, so let's try this and see what happens. Integer the numbers in the expression. P of T, 500, n to the power of T over 3. T over 3. Let's see, 500. Okay, so then T over 3, 3 years. Okay, no, that doesn't help. Okay, so let's go to view an example. So, okay, a quantity increases n-fold over time, blah, blah, blah. You're not doubling time, right? Okay. If they give us the doubling time, well, do we go into that? Let's see. Population double, so n is 2. Oh, okay, so this one's a little different. So then it looks like we just need to do a base of 2, right? So we're going to say 2 to the power, it should be T over 6 in this one. So ours would be, okay. So that's, so the only thing we're missing is that n is 2. That n, let's see. If a quantity increases n-fold over a fixed period of time T, so the little n in this case is like how much it increases over a period of time. So again, since we're doing doubling time, that means our n is 2. So the only change that we need to make is that n is 2. That's fine. Let's say times 2 to the power of this, right? Okay, that's fine. Now, let's go back. Now, in the more traditional, like this PERT formula. So we'll go ahead and make that change here. Right, it was 2, right, times. So then if we're working with P of T equals P naught E to the RT, all right, let's fill in what we have. Okay, so we know that the initial amount P naught was 500. E, the rate now, okay, again, now if we wanted to solve for the rate. So we said if we have the doubling time, then we have that there's a the doubling time formula or the half-life formula, KT equals the natural log of 2. This is where I was trying to start, but I was like, well, it didn't really apply to the first, but that's okay. So the doubling time we said was what, 3 years, right? So then if we want to solve for the rate, if we divide both sides by t, we would get the natural log of 2 over 3, right? So this is an expression for our rate. Sometimes I call it K. Okay, so we have our R. So I'm just going to leave it like that exact. I'm going to call it the natural log of 2 over 3. Okay. And then times T, right? And this is our P of T. Okay. Let me highlight these. Come on. Copy. Paste. And then let me kind of space this out a little bit. All right, that's better. Okay. So let's see how do we do here. 500e to the power of natural, let me see. And we probably should crunch that number around as round to 4 decimal places as needed. Okay. So the initial conditions, we have a 500. And then that rate we said was the natural log, natural log of 2 divided by 3. So we're gonna crunch that here. Natural log of 2 divided by 3. Okay. It says round to 4 decimal places, 2310. So 0.231. 231. Yep, there she goes. 0.231. She's definitely getting started. I swear it's like they'd be marching in the battle. It'd be like, and I know they're exercising, but I'm just like, yeesh. All right, next question. Okay. I'm tempted to give the backstory on where the half-life or doubling time formula comes from. And I probably will. I mean, I did it in the lecture. If anybody wants to see that, I will do it right now. Let me see. Let's try this one. Find an exponential function of this form that models the situation. And then, so basically it's a repeat, right? This one is the tripling time. Okay. Okay, so P naught, the initial population was 4,500. So we're gonna go ahead, we know that's a 4,500. N was I forget what it's called, but I just want to get the terminology right. Well, that's the 3, right? Let me just go ahead and do this first. 3 to the power of T over, let me see. And the tripling time was 5 months. Now, do we need to convert this to years? Usually, let me try 5. And if the 5 doesn't work, it might be a half. Because we might usually look like these formulas, the time needs to be in years, but sometimes they don't. I'm just going to go ahead and view. Oh, we don't have it? Okay. I was going to view an example. Let me see. 5 months. So it's either a 5 or a 0.5. Use integers or fractions for any numbers. Let's go ahead and convert months to years, because usually these are supposed to be in years. So if it's 5 months, then that's going to be 5 over 12. So you can say, kind of like this, 12 over 5. Let's try this. Okay, only other thing, instead of converting it to years, leave it in months. So I'm going to get rid of the 12. 4,500 for it to triple T. Let's go with it. Okay. Yeah, so this one they left it in months. That was my hesitation. That's fine. So we got there. And then find the equivalent. Okay, so then if we want to do it. Okay, so this one I'm gonna actually work this one all the way out. I'm gonna do this one a little bit different than I did the last one. So the doubling. Okay, I think with this one, I'm going to go ahead and give the backstory on the double time formula, the doubling time formula, and then we can transfer it to the tripling time. So let me get a copy, and we're going to take it from here, there. We can take all of this, I guess. So I'm going to give a little bit of context here. There it is. Okay. So first, let me start with some backstory on the doubling time. All right. So if we're working with the exponential growth model, right? So like we have A of t equals A naught e to the kt, right? So this is just like an exponential growth model. And suppose we're considering doubling time. Doubling, this is just backstory, the doubling time, right? So we're exploring how long it takes for something to double, right? So if we're considering how long it takes to double, that means if we start with A naught, we're going to finish with twice of A naught, right? We said how long? Okay. So then let's kind of do some simplifications here. So we can divide both sides by the A naught, right? That's just a number. So we can divide by both sides by that. So then we'll get 2 equals e to the kt. Suppose we wanted to solve for t, right? So then, I don't know why I switched my colors. So if we wanted to solve for t, we would take the natural log on both sides, right? That's where that natural log of 2 was coming from. So then natural log of e cancel. And if we were solving for t, well, that's as far as we really need to go. Because then we get to the point that kt, and I'm going to switch it to capital T for doubling time, equals the natural log of 2. So that's where you start before, right? So then it's like, if you wanted to know how long it took for something to double given a given rate, then you divide both sides by k. If you're giving the doubling time and you're trying to solve for the rate, you divide both sides by t, right? So I want to say if we wanted to extend this to tripling time, I think we only need to change that natural log of 2, just change it to a 3. But I'm going to work it out just to be sure. I'm going to do it in green. We're going to do for the tripling time, right? So say we want to talk about tripling. It's the same concept, tripling time, right? So then if we start with the exponential growth, e to the kt, let me go ahead and do capital T for tripling time or whatever. If we want to triple, so that means we're going to finish with 3 times A naught, right? So then if we do a similar thing, divide both sides by the starting amount, right? So then we get 3 equals e to the kt. Take the natural log on both sides, all right? And so all we had to do was change the 2 to a 3, and I think we were golden, right? So then we got kt equals the natural log of 3. Okay, so we can use this as like a tripling time. Okay, so then for our question, let me see. We had an initial population of 4,500 and the tripling time of 5 months. Okay, so we were given the A naught was 4,500 and the tripling time was 5 months. Okay, so then from there, with that, we can get the rate. So that means that our K is going to be what? The natural log of 3 over 5, right? So that's an expression for a k. You just crunch the number. Now, again, with these examples, we do not want to round into the end, right? If we crunch the number early and we cut that decimal too short, it's going to throw off a final answer. So if you do crunch the number and you use a decimal, write out the whole decimal. Just write out the long decimal. Keep doing that until you get to the very end. My way of writing out the whole decimal is keeping it in this form, right? I'll use this, and I'm going to put like this for reference. Okay. I think we are asked to find a model, right? So again, if we're using the exponential growth model, I think it was P of t equals P naught e to the kt, right? So then our P of t, let's plug in the parts. The initial was 4,500. E, we just got an expression for the rate. I think we can go ahead and crunch that number and simplify. So we can say the natural log of 3 divided by 5, okay? 3 decimal places is going to force the 7 to bump the 9 up, so that's just 0.22. 0.22, and the tripling time was 5 months. So let's just go ahead and say, wait a minute. No, we use the tripling time. We use the tripling time to solve for t. I mean, to solve for k. So this right here is actually lowercase t. Let me highlight the change. This is lowercase t. Okay, and then we're going to say this is times t. Okay, I think this is okay. Good about this. Now I know that may have been, I don't know if the speed was too much or anything. Just if I need to go back over any concept, just let me know and we can go back and talk about it. Like this, then okay. Okay, oh, and then like this. So let's give this a go and let's see how do we do. I had to give a little bit of okay. Oh, come on. It's all been a little bit tricky. Close this out and then hit this. Can I think there's a way I can stop that from automatically popping up. Give me a moment. Here it is. Keyboard accessibility. Turn it off. Because I think that's what's causing this to happen. Nope. Okay, let's do like this. That's gonna have to do for now. Okay. I can't see that. I think it's 4,500. There it is. Jeez. 4,500 e to the, I think we got 0.22. It says 4 decimal places. Let me look at that again if that's saying 4 decimal places. This one. So now, if we check our decimals, so part of this, I think, is because like I'm on Safari. Okay, so actually we need to say 2197, 0.2197, right? Because if we're going 4 decimal places, that puts us at that 2 to the right of 7. The 2 says to leave it at 7, right? I think I was doing 3 decimal places. Okay, I'm gonna go with this. See what happens. Okay, let me check Zoom to see if we got any people in the waiting room or anything. Okay, cool. We look good there. Okay, hit see. Let's hop back. Okay, another one. Let's get rid of this. Next question. Okay, so the derivative of the exponential function, right? Let's see. So it's very similar. In the past, we were talking about the derivative of e to the x, right? The derivative of e to the x was unique because It's its own derivative. So the derivative of e to the x is itself. This is the exact same with one additional part, right? So the derivative of the general exponential function is going to be itself times the natural log of the base. So times the natural log of 4, right? Because we were actually multiplying by the natural log of base before, but our base was e, right? So then the natural log of e is 1, so you don't really notice it, right? So again, we still hold that the derivative of the exponential is itself, but now we need to say add this extra component that says times the natural log of the base. All right, enter. Okay. So same thing here. The derivative of an exponential is going to be itself times the natural log of the base. Okay. Same thing here. 6 times 11 to the power of x times natural log of 11. Okay, just stop me from going too fast if we need to go back. Okay, let's do the same thing here. The derivative of an exponential is going to be itself, x to the power of 6. Man, that's a lot of exponents. Plus 3. Then we're going to say, wait a minute. So then we're going to still say times the natural log of the base, which is going to be 11. But then we also had to apply the chain rule. So we had to say times the derivative of the exponent. So times, in this case, it's going to be 6x. Right? 6x to the power of 5. Okay. If I need to go through any of those details, just let me know. If I need to write it out or redo it, okay. Let's keep it moving. You just have to unmute yourself to get my attention. Let me check the chat really quick. I think the chat is okay as well. On a derivative, so with constants, when you take a derivative, they just kind of sit out in front, right? They just persist. So that's all I did. The 950, the derivative of an exponential is itself, so I'm gonna say times this exponent, 1.661 to the power of t. And then we have to say times the natural log of that base, 1.661. Okay. All right. And we are like flying through these. Okay, so we have two terms that have variables, and we're differentiating. So we need to use the product rule. We have several rules that we're using at once here, but the main one is the product rule. So the way the product rule goes, again, as a recap, the first times the derivative of the second plus the second times the derivative of the first, right? So we're going to kind of take notes here. If I need to write this out, just let me know. The first, which is this guy, x to the power of 6, times the derivative of the second is going to be itself, okay, times the natural log of 2.1, right? The first times the derivative of the second plus the second, which is this, second times the derivative of the first, so we're going to say times 6x to the power of 5. The first times the derivative of the second plus the second times the derivative of the first. I think I'm just going to go with this. We could factor some stuff out. Let me leave it like this. Okay. Okay, so the last one we did the product rule. Now we're going to do the quotient rule. So the quotient rule goes, the way I remember it is low D high minus high D low over low low, right? So that's the bottom, which is this here. Let's put it in a fraction. So the bottom, which is this 7x plus 6, bottom times the derivative of the top. So let's just say times. So we're going to have 5 to the power of x times the natural log of 5. So the bottom times the derivative of the top minus the top times the derivative of the bottom. So it's just going to be times 7. Bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom square. 7x plus 6 quantity squared. Okay. Can't see anything else. Let's give it a go. All right. Next. So now, we've worked a few examples where we went over the derivative of a generic log. So now let's look at the derivative of generic. Sorry, we went through several examples where we worked over the derivative of generic exponentials. So now let's look at the derivative of generic logs, right? So in the past, when we did the derivative of the natural log or the common log base e, the derivative of the natural log was basically dx over x, right? So it was 1 over x times, times the derivative of x. So then this is the same thing, but we have to do a similar adjustment, like how we did for the common exponent. We do a similar adjustment. So then it's still dx over x, but then we say times 1 over the natural log of the base, right? So what I mean, let's see this in action. For instance, this derivative is still going to be 1 over x, but then we have to say times 1 over the natural log of 5. So we can put the natural log of 5 right here. Let's put it here, ln of 5, right? So we still did dx over x times 1 over the natural log of the base. Enter. Let's try that one. So dx over x. So then our dx is just going to be 6. So we got 6 on top. Dx over x, so that's going to be 6 over 6x minus 3. And then we have to say times 1 over the natural log of that base. So let's put this in parentheses. We could factor out a 3. If we factor out a 3, this is going to turn to a 2. This is going to turn to a 1. This turns to a 2, right? And then, again, we need to say times the natural log of 47. Natural log of 47. Okay. Let's go with it. Okay. So again, for log, it's dx over x times 1 over the natural log of base. So the only part we're changing from the previous discussion is that times 1 over the natural log. Okay, so dx, so the derivative, so dx is going to be, in this case, 6x to the power of 5 plus 1. Well, I probably should have hit my division a long time ago. Let's just start over. Fraction. We said 6x to the power of 5 plus 1. And then we keep the x to the power of 6 plus x. Okay. Dx over x times 1 over the natural log of the base. So nothing cancels. Okay, so we're going to say times the natural log of 5. Okay. We are like flying through these. I don't want to let you guys go that early. I mean, I'm sure you guys probably wouldn't oppose to it. I mean, and again, this is still asynchronous, so you don't even have to be here, but I feel like I wouldn't be doing my job if I didn't make myself available. Let's keep going. Again, as long as you check in and get your stuff submitted, that's all I need from you. Okay, so the product rule, right? Anybody want to give this a go? Do we have any? Let me see. Anybody feeling froggy, confident? We got a good amount of people. Anybody want to give it a try? Okay, so the product rule, right? Let's do the product rule. The first, which is this guy, 10 to the power of x, first times the derivative of the second. So that's going to be dx over x. So let me see, let's say times, this is going to be 1 over x times the natural log of 4. Okay. So that's the first times the derivative of the second plus the second first times the derivative of the second plus the second times the derivative of the first. Okay, so we're going to hit time. So the derivative of 10 to the power of x is going to be itself. And we got to say times the natural log of 10. Okay. Let's see. Okay. Another one. On to the next one. Okay, let's look here. It says the population of Neelam doubles in size every 3 years. In 1992, its population was 15,000. Find an exponential function of this form. I think we can do this quickly. Let's see how quickly we can do this right here. Well, it's not about speed. Find the exponential function. Okay, so P naught doubles in size every 3 years. 1992 is 15,000. So we're going to treat 1992 as our starting year. It says doubles, so that means our n, we're going to say times 2 to the power of, and the doubling time was 3 years, so we're going to say 2 to the power of 3. 3 years, all right? Use integers or fractions or any numbers in the expression, and we need a t. N was 2t over 3. T over 3. Okay. Okay. I think this is okay. Let's hit enter. Find the equivalent exponential model of this form. Okay. So then our starting amount was 15,000. 1, 2, 3. Okay. So then for the k, all right. So for the k, it says round to 4 decimal places. So we can use that doubling time formula, kt, and it's, let me see, doubles. So we could say kt equals a natural log of 2. If the doubling time is 3, so then that means our rate is going to be the natural log of 2 divided by 3, right? So let's do the natural log of 2 divided by 3. Let's do, come on. We said the natural log of 2 divided by 3. And it says around the 4 decimal places is needed, 2310. Let's do, okay, let's do that. 2310, 0.2.31. Okay. Okay. So this is kind of like a repeat of what we did earlier. That's why I didn't write it all the way out. What is Neelam's yearly percentage growth rate? So the rate of growth, when you go to take, I think the whole point of this was that the derivative of this is going to be the original function times the rate. So if we just round the 2 decimal places, I think, well, we have this, right? So I guess we let the time be 1 year, and we let t be 1 and multiply by the rate. Let's try that and see what happens. So long story short, let's do 15,000 times e to the 0.231, right? And then we're going to say times 0.231. Okay, so then it should, no, that can be right. Let me think about it. 0.231. Let me see, can I give you an example? Hang on, before I do that. $2021, okay, I mean 2001. Okay, I'm going to view an example. So I just want to hop to the end of part C. Mhm. Okay, so it says the yearly percentage growth rate can be read from part B. It is the coefficient of t in the exponent, okay, multiplied by 100. Okay, okay. Well, we totally overthought that. So the growth rate, right? We have it multiplied by 100, so 23.1. Let me see. I'm gonna go back to the previous one. Enter 23, yeah, 23.1, two decimal places. Okay, totally misread that. 23.1. The population in 2001 is blank people. So then we have this, so we can just, if we started in 1992, 2001, is that 9 years later? So we just need to let t be 9. Okay. So what I'm going to do, I'm going to go over here to the y equals, and I'm going to put the function that we found. It's 15,000 times e to the power of 0.231 times, I'm going to put x, right, for my t. I think this is okay. I'm going to quit. And then I'm going to call on that function. So to the left of the clear button is a button that says VARS, so variables. I'm going to go to the right to Y variables, number 1 for function. And I'm going to call on that function that I just typed in. And we said let t be 9. Now, what we could also do, if we want the year 2001, we can say 2001 minus the starting year was 1992. Right? And that way it'll calculate it for us and put that answer into the function. Let's see. If we started with 15,000, 100, nearly 120,000, it doubles in size. Is that reasonable? Every 3 years, and it's been 9 years. 15, 30. Yeah, I guess I can get up there. Let's give it a go. Doesn't say anything. Let's do 119,947. 119,947. 119,947. Okay. Oh, without using a calculator. Oh, okay, that's fine. Okay, so here, if we use that doubling time, I didn't see that without a calculator. Right? Oh, let's go like this. Oh, it's being kind of tricky. Here, let's zoom out. Sometimes that helps too. Okay. So if it's doubling every 3 years, right? So then, for instance, if we started with 15, after 3 years where it's at 30, and then another 3 years where it's 60, so then 120. 120, 1, 2, 3. Okay, so again, we use the calculator. They want it without. Yeah, again, I just didn't see that without the calculator part. Okay, that should be it. And then Neo's population was growing at a rate of blank in 2002. Do not round to the final answer. So in 2002, we can plug that in. And if we want the rate of growth in 2002, we just say times the growth rate, right? So we get our answer, we plug in 2002, and then we say times the growth rate. So what I'm going to do, this does not have the growth rate. So I'm going to recall this function that we had before. We're going to change it from 2001 to 2002. And then I'm going to say times the growth rate, which is, I think it was 0.231. Yeah, 0.231. So I'm going to say times 0.231. Okay. So the rate of growth in that year was 34,000 people per year. Do not round to then round to the nearest whole number. So 34,908. 34,908 people per year. Persons per year, right? This one. Okay, let's go with that. Let's check. That was an adventure. But that's how it goes. Like, that's the purpose of the homework. That's why you use Pearson. Like, if you get stuck, like by now you should see why I kind of set everything up the way it is, because like, even like, for instance, I got stuck. So I was like, well, let me check something, right? Let me look. It's all right there, right? Most of the time. Now, for instance, this one, we don't have that support right there with the question, but I think we had it with the last one, and I think this one is similar, right? So a lot of the questions have the support right there next to the question. So we might piggyback off the previous one for this one. So let's just see how it goes. So it says in 2012, 34% of all glass containers were recycled. A beverage company used 300,000 pounds of glass containers per year. After recycling, the amount of glass in pounds is still in use after 2 years is given by this. N of 6, and explain this meaning. Round to 2 decimal places is needed. So it looks like we just plug in when N is 6, right? So let's do that and see what happens. So then I'm going to go to this y equal, and I'm going to put this in 300,000, 300, 1, 2, 3 times 0.333 to the power of t. Oh, it's time to wrap up. Okay, we're going to try to get to this last one, to the power, I'm going to say, of x. Okay. I'm going to recall that function, variables, y variables, and when t is 6. Okay. Pounds. It says, let's see, we got round to 2 decimal places, so 0.6, 409, 0.6, 409.06. Okay. Now it says that after recycling, the amount of glass in pounds still in use after 2 years is given by this. So this expression means that after 6 years, the amount of glass still in use is the amount of glass is still used after 2 years. No, it's not a rate. It's not a derivative. It's not pounds per year. It says the amount of glass in pounds still in use. I'm going to say is this one. Let's do this one. Okay. So then that's the rate, right? So n prime. So if this is the amount of glass still in use is n of 6 pounds, this is going to be the rate of change. Let me see. So that derivative, so it's this times the exponential and then times the natural log of base. Okay. So then all we need, we can take our answer and say times the natural log of 0.33, right? So let's do like this, times the natural log of 0.333. Okay. 2 decimal places. So that's the rate. So that's how much is decreasing. That's how many pounds is decreasing per year in that year. All right. So then a negative, it says 2 decimal places, 81, 449.81, negative 449.81. This should be pounds per year. After 6 years, the amount of glass still in use is decreasing. It's changing by in prime pounds per year. This one. Let's check that. Let's get the time. Okay. It says when 6% of the original amount of glass, when will, right? So they're asking us to solve for T. When will 6% of the original amount of glass still be in use? Per year, right? When will 6%? So we want to finish with, so if we started with 300, we want to finish with, I kind of want to write that one out. We want to finish with 6%, right? So 6% of 300,000. Let's just do that over here really quickly. 300, 1, 2, 3 times 6% is 0.06. So when 18,000 pounds, when we finish with 18,000. Let me see. Yeah, let me write it out instead of trying to force it. So let me get a copy. We'll go from here. And we're really just working on part C. That's fine. I think this is you guys. Yeah. Okay. All right. Let me see. So when, okay, so we found that 6% of the 300,000 was 18,000. I don't know what's going on with my pen. I think I need to restart the tablet because the pen is fully charged. So I was like, I don't know why it's gonna throw in a tantrum. Okay. So we want to finish with, so let me see. If we have this 300, and this will be it. Like once we finish this, I'll let you guys go. Oh yeah, let me choose this class. Sure. This is fine. I don't think it's doing it, but it's okay. Okay. So we have this 300, 1, 2, 3 times 0.333 to the power of T. We're solving for T. And we want to finish with 18,000, right? So we can divide both sides by that 300, 333 to the power of, to the power of T. So if we divide by 300, we at least have 18 over 300. I just cut off the trailing zeros. We can divide both. We can divide both of these by 3. Let's see, 6 over 100. If you divide by 2, 3 over 50. Okay. Okay. So, right. So then to solve for T, we take the natural log on both sides to get it out of the exponent. All right. This is going to come in front. So then this gives us T times the natural log of this 0.333 equals the natural log of 3 over 50. Okay. So then long story short, T equals the natural log of 3 over 50 divided by the natural log of 1, 2, 3. Okay. So if we crunch that number, we're gonna say, can I just do a button? Nope. It's the home button. It's math. It's negative. Okay, sorry. Trying to see if I can type, because I know you can type on this, but anyway, I'll figure it out later. LM, what is it? I used to have all that is that? Okay, what if I hit shift? Oh, there it is. Wait, oh my goodness, how do I go back? Oh, I hit something. No, it's not that one. What's clear? See? Nope. I figured that out later. Let me get back. I had, okay, in a second. Oh, I see. E? Nope. Okay, forget it. Okay. Natural log 3/50. I think I could type 3 over, no. Okay, I found a clear button. Natural log of 3. Okay, forget it. I'm still intent on trying to figure out these shortcuts. Natural log of 3/50 divided by the natural log of 1, 1, 2, 3. Okay. All right. Let's hop back here like this. No. I want this one to be full screen. Okay. Pull this guy up. So it says 6% of the original will be still in use after. Let's see how I feel about this. No, I'm not confident in this. I don't like, it feels off. 6% of the original models will be used after 2.56 years. Let's give it a go. I think I know where I made my mistake. If there is an error. I think it's at 2.56. 2.56. Yeah, let's see. Okay, well, never mind. Okay, so that is a good place to stop. All right, so we got through as many questions as we could. I know it's a little bit choppy. Let me go ahead and share this with you guys. I'll send it a box, but not for college algebra. Calculus. Answer homework questions, and I'll put it there. Okay. Yeah, if there aren't any burning questions, we're going to end the session here. Okay. Let me think about, let's see. So that brings us to the end of chapter 2. So that means we're ready for exam 1. Exam 1 should become available this upcoming Monday at the start of class, and it'll be available for 7 days, right? Also, I think the exam has prerequisites, so you definitely want to make sure you score at least 50% on all the previous assignments. So if you're not up to date, you definitely want to just go ahead and get up to date. You don't want to wait until the exam becomes available and then you can't access it. So now you're decreasing the amount of time you have to get above a 90. Yeah, and so then next week I'll probably just be available for questions, so we can use class time. You can ask me questions about anything, the exam, the quizzes, the homework. All right, it's just trying to get you guys up to speed and get caught up. We're just using it as a study session or a Q&A. Next week, if you don't have questions, I'm just going to hang out on the call, but I won't probably be talking a lot. Okay. So with that, again, if there aren't any burning questions, we're going to end the session here. And from one beautiful mind to another, enjoy the rest of your day. Take care, guys. Peace. Let's see. Got a few people hanging out.